These are practice problems from section 12.5.2, which covers three-dimensional lines. The first practice problem is number 8. We want to find the equation of the line through the point 1, 0, 3, and perpendicular to this plane, x plus 2y minus z equals 1. Well, in order to find the equation for a line, we need two things. We need a vector that runs in the direction of the line, and we need a point. So we've got the point, and we can get the vector that runs in the direction of the line here. Because the line I want is perpendicular to this plane, the normal for the plane will act as that vector that runs in the direction of the line. Of course, that normal in this case is equal to 1, 2, negative 1. So I want an equation for a line that runs in this direction and goes through this point. So here's how we write it. The vector version of the equation for a line begins with a vector that runs from the origin to a point on the line. In this case, that's 1, 0, 3. So the vector will be 1, 0, 3 because that's a vector that runs from the origin to that point. Next, I want to invent the parameter t, which is going to act as a multiplier for the vector direction, which is 1, 2, negative 1. Now as t takes on different values, it basically moves in the direction of the line from this point. So as t takes on positive or negative values, it moves away from the endpoint of the directed vector along this direction. And as long as t can take on any value, it will actually define every single point that lies on the line in 3 dimensions. Now this isn't the only version of the equation for a line. This is called the vector equation for a line. I can also pull out each one of the 3 parametric equations separately. This is what that would look like. The x-coordinate will be the location 1 plus t, because it's 1 times t for the direction. This will generate all of the x-coordinates as t takes on different values. The y-coordinates will be generated by 0 plus 2t. Again, as t takes on different values, this will generate all of the y-coordinates. And finally, the z-coordinate. The z-coordinate of every point on the line is going to be 3 minus t. And as t takes on different values, this will form all of the z-coordinates. So this is the second form of the equation for a line. This is the vector form, and this is called the parametric form because it features that parameter t. The final form is if I solve for t in all 3 of these and I set them all equal to each other. That's called the symmetric form of the equation for a line. If I take x minus 1, that will be equal to t. So that's the first term, is x minus 1. And that will be equal to y divided by 2. So y divided by 2. And then that will be equal to z 3 minus z, because we want the t to be positive to be able to be equal to these two. So I move the t over and I move the z back, so it will be 3 minus z. No denominator on this one. And this is the symmetric form of the equation for a line. Basically, any points x, y, z that satisfy this equation will then be points that lie on this line. So there it is. There's the vector form of the equation for the line, the parametric form, and the symmetric form, but they all represent the same thing. It's the equation for the line that's perpendicular to this plane and runs through this point.